Hello, I'm Anıl Akağaç. I'm about to make a presentation about nanotechnology in textiles. Nanotechnology is the design, characterization, production, and application of structures, devices, and systems by controlling shape and size of building blocks at the nanometer scales. We can talk about three types of nanotechnology in textiles: nanotechnology in fibers and yarns, nanotechnology in coatings, and e-textiles. A nanofiber is a continuous fiber which has a diameter in the range of billionths of a meter. The smallest nanofibers made today are between 1.5 and 1.75 nanometers. Nanoscale materials can be rationally designed to exhibit novel and significantly improved physical, chemical, and biological properties because of their size. When particle size reduced to nanometer range, there can be some dramatic changes. Normal ceramic particles are brittle, but nanoceramic particles are flexible. Or normal gold particles are yellow, but nanogold particles are red. At the production of fabrics, when we use conventional methods, they will lose their functions after several laundering or wearing. They will lose their breathability and comfort. But with nanotechnology, we can provide high durability for fabrics because nanoparticles have a large surface area to volume ratio and high surface energy. There are three different structure types of nanoparticles in textile: whiskers, nets, and wraps. Whiskers, the whiskers get hooked on the fibers to alter the fabric property. Whiskers can make the fabric stain and water resistant. Whiskers have some value additions to fabric like water and oil repellency, superior durability or breathable. The second structure is the net. Three-dimensional molecular nanonet covers the core fiber completely. Nanonet have some value additions, of course. Nanonets alters the property of synthetic fibers like polyester to give a feel of cotton and linen. Wicks body moisture fast and dries quickly and gives the cooling effect. The third structure is the wrap. Nanosheet wraps the fiber completely to cover it and alter its property. Nanowraps can enhance the fabric wash fastness. There are some value additions due to nanowraps, like strength and durability, improvement in color fastness, crease retention, and static resistance. You can see here some nanoparticles like clay nanoparticles or magnesium oxide nanoparticles and silver nanoparticles. Here we can see the diagram of textile applications of nanotechnology. Nanoparticles can be introduced in the textile production process at two levels. First, during the melt extrusion of yarns, or during the coating. There are three types of application. First, the fabric is padded and dried, or during drying, water evaporates, or during subsequent curing operation, the polymers melt and spread, giving uniform coating of fibers due to nanosize of the finishing agent. For antibacterial and deodorant finishes, there is a silver fresh application. Silver fresh's typical example is when human body perspires the clothing in contact with skin, such as socks or shirts. Smell due to growth of bacteria. This drawback is eliminated by silver fresh finish. Incorporate silver particles in a size of around 4 nanometers into fiber. A material of superior antibacterial deodorant properties with good laundering fastness has been brought about by letting silver particles penetrate into the fiber itself. We can see illustration of silver nanoparticle penetration in the fiber. The metal ions catalyze the production of oxygen radicals that oxidize molecular structure of bacteria. The silver fresh antibacterial deodorant finish has been developed for use mainly in garments worn close to skin. Further applications of this technology are being planned for use in uniforms, casual wear, shirts, beddings, nightwear, and underwears. Titanium dioxide nanoparticles are catalysts that help break down carbon-based molecules, require only sunlight to trigger the reaction. The inventors believed that these fabrics could be made into self-cleaning clothes that tackle dirt, environmental pollutants, and harmful microorganisms. The titanium dioxide particles covering the fibers are 20 nanometer size. Hydrophobic finishes lower the surface energy and can give a maximum water contact angle of roughly 120 degrees. To get higher contact angle and to have the self-cleaning ability, surfaces with contact angle between 150 to 180 degrees are required. Nanosphere impregnation involves a three-dimensional surface structure with gel-forming additives which repel water and prevent dirt particles from attaching themselves. This property is comparable to some phenomena in nature, such as the leaves of the lotus plant. Smart interactive textiles are materials and structures that sense and react to environmental conditions such as mechanical, thermal, chemical, electrical, magnetic, or other sources. Applications of nanotechnology in military science: military uniforms that change color to match the environment, lightweight bulletproof vests, manipulating light so soldiers seem to disappear. Scientists are also working on electronic camouflage fabric which changes the colors instantly to blend in with the surroundings. In addition, sensors would provide the soldiers' vital signs and location to medics via radio. Until the new nanosensored garment is ready, soldiers will wear an adhesive chest patch fitted with sensors and a tiny radio. If a soldier is injured in the arm or leg, the fabric would constrict into a tourniquet. This will be a real lifesaver, because half of all battlefield deaths are due to massive blood loss before wounded soldiers can be treated. Global Positioning System. Textiles integrated with sensory devices driven by a GPS can detect a user's exact location anytime in any weather. Interactive electronic textiles with integrated GPS enhance safety by quickly locating the wearer and allowing the suit to be heated. GPS can provide added safety for firefighters and emergency personnel by facilitating off-site monitoring of vitals. A combination of sensors and small flexible light emitting displays can receive and respond to stimuli from the body, enabling a warning signal to be displayed or sent. The sensors can monitor heart rate, respiration, and temperature. If vital signals where below critical values, a flag would automatically display, for example, a flashing red light, and a wireless communication system could send a distress signal to a remote location. Thanks for listening. By the way, the references are here at the end of the presentation.